to achieve this. So the issue is complexity control. How can we sort of do this in a reasonable amount of time, in our lifetime, sort of, or in a few years? Sort of my hypothesis, which I think at least a few others share, is sort of you base this on a few conceptually simple primitives, and then you sort of have control over those, and then you can sort of by combining these to span the whole problem and to span many problems. So we try to sort of avoid one method for each problem. The second part is that we try to avoid premature optimization. So if you optimize something sort of in the beginning, it becomes more complex, and then in the end it might not even have, it might not even be important, it might not even be used. And then, so sort of this is also an important part, which I think is relevant here. So sort of if we look on the application level, if you try to validate an application and then you rely on a whole tool chain, then it's important that sort of software interfaces are stable, and sort of also software implementation, but primarily the interfaces, so that at least you can do sort of the codes, you have code stability. So this, I will discuss this one more point a little bit further. And then the driving force for the technology development is applications. So this unified continuum technology, it's basically just conservation laws for momentum, and here it's incompressible, so we have conservation of momentum. So here is the equation and discretization, or the weak form and discretization of the momentum equation. And then the idea, let's see if this can work again. Yes. So then the idea of this unified continuum sort of is to treat stress as data. So we sort of just have the stress as a symbol, as an object, and then the conservation of momentum sort of looks the same for different phases, fluid or structure. So here we have some S here, the stress, and then we try to keep a sort of abstraction of time stepping, or for time-dependent PD. So we have sort of the time derivative, and then we have, this is our sort of equation without the time derivative, f of u. So this is f of u. So this is the weak form with the discretization, then, so we have stabilization terms. And I have omitted here the finite element declarations. So P1 here. So here we have this stress term. Here we have this convection term. And we have some force term and so on. And we do this with fixed point iteration with a Newton type fixed point method. So we have some approximation, the Jacobian and so on. And this would be interesting with this UFL, for example, to compute that automatically. And this is then the equation for time step. So we can call this a monolithic method. So we have the same discretization for the whole domain. So this is sort of a hat function here. So it spans the two phases. So we sort of discretize everything as one. And the idea then is this allows treatment of these sort of models by standard methods for error estimation, adaptivity, and sort of standard stability arguments. We just can use exactly the same ideas. Then we have, this is in Euler coordinates, so sort of everything is in laboratory coordinates. And we have a moving mesh for tracking solid fluid interface sharply. And then this sort of method is this G2, so the stabilization and so on is the same as in previous work. So then the status of this, I can just check the time. Status of this is we've done validation against a 2D benchmark, laminar from Turek paper. We have sort of robust mesh smoothing where we solve a similar elastic equation. So we use sort of the same unified continuum formulation for solving a problem with a mesh. And this general time stepping abstraction. We've done some sort of work on this efficient Newton type fixed point iteration. We have that in a report. And the sort of mode of operation is that we fixate sort of a version of FEniCS and work against that, where we have a stable interface then. So that we can isolate sort of where problems occur in our and also interfaces. And on the to-do list, we want to solve dual problems. We don't do that for adaptivity. And for to be able to achieve turbulence prediction for turbulent flow, we think this will sort of be the missing piece, friction boundary layer modeling. And parallelization of the mesh motion seems to also be an issue that will come up. Okay, so we've also done to see that the whole sort of machinery works in a robust way, and also sort of as an initial step toward turbulence, turbulent fluid structure. We have looked at a flag problem. So we have a fixed cube here, so and a flag behind this cube, which is flexible, and then we have a mean flow here. So the cube then generates a turbulent wake, then the flag then is oscillating in this wake. And here we have only mesh smoothing using this elastic analogy. And here we see an isosurface of the pressure, so low pressure then. So here we can see that this mesh smoothing is sort of robust and keeps at least a reasonable control of the cell shape and so on. But here the sort of accuracy of the prediction, here we just use no slip boundary conditions. So to be able to get convergence in this, we would need to refine further than computer power exists today. So it would take, we would have to wait 20 years or something like that.